Hello everyone, welcome to my presentation today. I'm Zhu from Technical University of Munich. The topic of my presentation is MINDflow-based dance matching between thermal infrared images and RGB images. First of all, why we want to matching these two kinds of data? The thermal infrared images record the temperature and emission properties of the object independent of its color on the surface. In this case, even different materials with similar textures can be easily distinguished. Secondly, it is used to monitoring the status of the object, such as starting cars with heated exhaust or parking cars. Thirdly, it provides a non-destructive way to detect the inner structures of the buildings, such as pipelines. So it can be used to monitoring building energy efficiency and detecting the possible energy leakage location. However, the interpretation of thermal infrared images requires certain understanding of the target scene and professional knowledge about thermal interpretation. In this case, the RGB images helped. Multi-source data registration is a hot topic and has been studied for some time. It targets to combine information from different platforms and sensors. Therefore, combining thermal infrared images and RGB images can provide a new visualization with multidimensional information for better scene interpretation and other tasks such as classification and segmentation. There are some problems we need to consider for matching these two kinds of images. Here is an example of the RGB image and the thermal infrared image. First of all, due to the different wavelengths used by different data, the intensity distortion can be clearly observed between them. There is no linear or certain model to describe the intensity relationship between these two kinds of data. Besides, the thermal infrared images had blurry features compared to the optical images. Secondly, due to the sensitivity of the camera sensors or the parameters for the cameras, the scales may differ. If the optical camera and the thermographic camera are not mounted on the same platform, the translation and rotation need to be calculated for every corresponding image pulse. Besides, the overlap between every two image pulses may differ. Here we propose a method for matching the RGB images and the thermal infrared images. Here is a workflow. First, the orientation and the scale is estimated based on the result of phase congruency. Then, mobility-independent neighborhood descriptor is used to calculate the features for each pixel in the RGB image and the thermal infrared image. Based on the result, the dense matching of corresponding points are conducted by MINDflow. Finally, the transformation using corresponding points are conducted, and the parameters are calculated. Then we come to the details for each step. Considering the blurry features of the thermal infrared images may influence the feature description result, the phase congruency was conducted to the RGB images and thermal infrared images to detect the notable edges or points in the image first. Phase congruency is calculated via local frequency analysis, which originated from local energy model. It assumed that perceived features are located at points where the Fourier components are maximum in phase. Since it's not robust to noise and does not consider the frequency spread, the algorithm refined by calculating model using low gamma wavelength are adopted. After calculation of the phase congruency, the scales of the orientations of the images will be estimated. The orientation of phase congruency can be achieved by the logo gap odd symmetric wavelengths of multiple directions, and the orientation of the image can be calculated by the accumulated orientation. To calculate the scales for the RGB images and thermal infrared image, the pyramid images was conducted separately. The optimal scales was calculated by finding the maximum normalization correlation coefficients between each image pairs. After applying the scale and orientation parameters to the image, we use the MIND to describe the features for each pixel. MIND, which represents a modality-independent neighborhood descriptor, uses the principle of local self-similarity. The first equation shows the calculation equation of MIND descriptor. In the numerator is a patch distance calculated as the sum of square distance between two voxels, and in the denominator is the variance of the images calculated via means of patch distance themselves. In order to highlight the response of MIND with similarity patches, a Gaussian function is used. After calculation the future descriptors for each pixel in the thermal infrared images and RGB images, a MINDflow adopted from the SwiftFlow was used to calculate the corresponding points between these two kinds of data. The energy function composed of three terms, namely data term, small displacement term, and smoothness term. The data term contains the MIND descriptor to be matched along with the flow vector. The small displaced term constrains the flow vector to be as small as possible when no information is available. The smoothness term constrains the flow vector of adjacent pixel to be similar. L1 norm are used in the data term and the smoothness term to account for matching outliers and flow discontinuity. The energy function can be then solved by the use of sequential Belief propagation. The experimental data used consists of two datasets, RGB images and thermal infrared images. Two UAV flights with the same predefined flight paths have been performed, one with the optical camera and one with the thermographic camera. We select parts of our result to be shown here. First, the RGB images are much larger than the thermal infrared images. By checking the first image pulse, a clear orientation difference and intensity difference can be observed. In order to evaluate the performance of our algorithm, we compile it with the SwiftFlow. In the first test image pulse, the SwiftFlow cannot give us a correct matching result, while our MINDflow can give an optimal matching result by checking the border of the rows. In the second image pulse, though the SwiftFlow can give us an approximate matching result, our algorithm gives us the optimal result by keeping the rectangle shape of the box. Finally, let's draw some conclusions about our work. In this paper, we propose a strategy to register thermal infrared images and RGB images based on MINDflow. It is able to achieve an optimal result in the images with significant features. And comparing it with SwiftFlow, our algorithm can extract the features for dense matching. However, it can hardly deal with the area with repeat patterns or insufficient structure differences. Therefore, the future work can be done on two folds. Optimal orientation and scale estimation for multimodal images, and the overlapping percentage of image pairs will be further studied. Thanks for your attention.